Hello, in this video, I am going to explain about the turning process, various different types of turning and various aspects of turning, understanding the process so that we can make the turning process more effective. This I have been presented in the form of PPT now, which I can show you. Then I can share that screen here, right? Okay. Now, yes. So this is the basic theoretical way of expressing the turning now. The job is rotating, the tool is not rotating. The tool is moved in the direction of the axis of rotation of the job. That is how the circular form is made on the lathe. You can understand go through the formula, the definition here. Turning is a machining process in which cutting tool is non-rotating, describes a helical path, and more or less tool moves on a linear path while the workpiece rotates, which has been very clear in the diagram. So this is how the turning process, this is how the theory of turning now. Okay. Now let us understand the machine. This is a CNC machine where you can CNC control is here, direct is here, the job is rotating and the tool is non-rotating and it moves to make the required form. You can understand the job is rotating, held on a chuck, and the tool is moving on the linear direction of the rotation of the job, and the turning is taking place, you can see clearly. This is the facing operation, and the facing is another operation in a turning. The third one is a boring operation. There are three: turning, facing, and boring. So this is a boring operation. This boring operation is making the hole in a more accurate way we can make it. So these are the three operations which are essential in turning, right? So let us come to understanding of the unit of measurement. That's a basic terminologies. In this video, I made everything in a metric form. That means to say millimeters, meters, Pascal, Newton, only those terminology be used, not the inches kind of unit to be used on this. Cutting speed is something which is in the unit of meter per minute. That is surface speed. That means nothing but the material is cut at surface at a particular speed. That is what is called cutting speed, which normally given by a tool manufacturer. Spindle speed is the one we have to set on the machine, which is number of rotation per minute. So this you have to calculate and put on this on the machine to feed on the machine. So this is a cutting speed formula which every engineer, even at the midnight when you wake up, you should know this. Very simple formula. Cutting speed equal to pi d n by 1000. 1000 is nothing but conversion of millimeter to meter because cutting speed is in meter per minute. D is in millimeter, N is in revolution per minute. So we can either, if you know the cutting speed, which is given by a tool manufacturer, we calculate the RPM, or if you know the RPM, calculate the cutting speed. Vice versa, we can do that. There are two types of feeds here. One is the linear feed, and nothing but the distance in which the rate in which the tool is moving. That is how many millimeters per minute it moves. And the another feed is rotational feed. How much millimeter it moves per revolution is called rotational feed. These have a relationship. Linear feed equal to rotational speed into rotational feed. Rotational speed nothing but a revolution, RPM. Okay. Rotational speed is how much millimeter move per revolution. If you multiply both, naturally we'll get a linear feed. That is what has been described here. Linear feed equal to revolution per minute, and rotational feed is millimeter per revolution. So this revolution get cancelled, you will get a millimeter per minute. Understand this in the logical sequence so that you don't forget the formula. If you try to remember this formula, you make a mistake. Let us be very careful about it. So the length of travel is required to calculate the cycle time required to conduct particular operation. Let us come to cycle time calculation now. The cycle time calculation is equal to distance, how much the tool traveled, I mean how much material removed, divided by linear feet. Okay, that is nothing but you convert it into millimeter divided by mm per minute. When you resolve this one by this thing, you will get mm get cancelled, you'll get a minute. So this also you have to understand the logical sequence of this, so that this is simple logic. You don't have to remember this formula and you can able to apply it for various operations. Now we can see this is that simple turning operation, wherein in the facing operation, the radius is nothing but a distance traveled. Okay, for cycle time calculation. In the OD operation, how much length you cut it, so that determines your cycle time. Okay, so this is a profile turning we can do. Various profiles can be turned internally, externally, but you have to make a proper tool selection which will not foul the component while doing the operation now. So this is the grooving operation which can be made in the OD, can be ID for a circle, for o-ring or whatever, we can do that. So this is a threading operation which can be performed in a lathe. Okay. And this is the parting operation. You can see this is held, this is a bar which is held on the chuck, and after the turning is completely over, now this is being parted off. Now the tool will be, component will be parted off. This is the drilling operation, which from the solid you can do the drilling. After the drilling is over, we can do the boring operation. So these are all the various operations on turning. Now let us come to power calculation. Power in kilowatt. Okay. Now this is a depth of cut, and this is the mm per minute feed. Sorry, mm per revolution feed, and this is the cutting speed, and this is the material factor for specific cutting force. Okay, which is megapascal. Divided by 60,000 into N. So this is a fundamental formula we have to understand. How do you remember the formula? You can see depth of cut normally we need for turning. This is the feed. Normally feeds are being given in mm per revolution only in a lathe. So this is a cutting speed which is there. This is constant. This constant, you can see the material. If it is a mild steel, lower value. If it is the alloy steel, middle value. If it is going to be a through hardening steel like EN31, it is a higher value. With this formula, you can logically remember, which is much easier to adapt. So I have given a general value for the quick calculation of cutting forces. Kc value for free cutting material is 1600 megapascal. For example, free cutting steel like EN1A and EN8, this is 1600. Kc value for low carbon steel is 1800 megapascal. Kc value for medium carbon and alloy steel is 2000. Kc value for through hardened material like 2200, like material like EN19, EN31 and all that, it will get a 2200 as a value. Please note, these are all not a very accurate value, but it's a suggested value by me, which I used it effectively. I found it is really more or less very close value, which is sufficient for any shop floor calculation to understand the power and calculate the torque required. Now, this is how the cutting tool manufacturer gives the Kc value. You can see here, all the materials are listed here, and then corresponding tensile strength of the material. And for each feed, type of feed, how much Kc value can be given. This much accuracy is not required. Whatever recommended in the previous slide, that is sufficient for us to calculate and move forward. So this is the relationship between power and the torque. Okay, this is also every engineer must know. This is a common formula for any manufacturing operations or forces. So this is nothing but the power equal to 2 pi nt by 60,000 into efficiency. So N is RPM, we already know about it. We know the power now with the previous calculations. So we can calculate how much torque required in operation, so that we can calculate the clamping force required and how much torque the motor of the spindle has got on the machine, so that we know the capacity and capability of the machine also it can be find out. Once we know the torque is equal to force into distance. Distance in a turning is radius. And that radius is in meters we have to calculate, and F comes in Newton. So we can always calculate how much force is coming out at the cutting point. With this, we have to calculate with the safety factor 1, 1.5 or 2, or depend upon situation. We have to calculate and apply the clamping force. If it is going to be very small material like aluminum or a copper, then the clamping force has to be adequate. Otherwise, it will go into the component. For that kind of turning, it is very much essential here. Okay, I hope I explained about the turning, various type of turning, the aspects of turning, and the formula required to understand, make the turning more effective. I request you to go through this video several times, so that it goes and sink into you, so that any point of time without referring, you will be able to use it and operate it and make the operation more effective. Thank you very much.